Hello everyone, and welcome to week 5 lecture on process heat transfer, that is heat transfer by radiation mechanism. My name is Dr. Salman Shahid, and from this lecture onward, I will be delivering the rest of the course on process heat transfer. So in terms of the intended learning outcomes of today's lecture, so by the end of this lecture, you should be able to explain what is radiation heat transfer and some of the governing equations that we use to describe this mechanism of heat transfer. You should be able to explain what is black body and gray body and what are the different properties like emissivity and absorptivity. And finally, you should be able to perform some basic calculation to see that for an enclosed system, how we can actually calculate the heat transfer between an object and its surroundings. So let's look at the mechanism of heat transfer by radiation. So Dr. Veni has already explained to you what is radiation. Okay, so radiation is a mechanism of heat in which the heat transfer is actually caused by electromagnetic waves, okay, or by radiations. And so one of the example of that is, for example, if you go for camping and if you light up the fire, you will see that a person who is standing far from the fire will also feel the warmth of the fire, and that is actually due to radiation. Okay, a person that is standing close to it will feel heat because of convection, or if it is holding the person is holding, for example, a rod next to the fire, it will feel heat due to conduction. But if you are far away from the fire, the heat is being transferred due to the radiation. Okay, so radiation is different from the other two mechanisms of conduction. So for example, conduction requires a solid medium for heat transfer, like in this case, this rod here. And for convection, we also need a medium, for example, the molecules or the air or the fluid or gases. So both these mechanisms require the presence of medium, while for the case of radiation, we do not require any presence of medium. So radiation is quite common in our homes and also in industry. So for example, if we look at this example here, some people are still burning, for example, have wood burners. They use them in winter to generate heat. And if you are burning this wood, for example, so you are heating your home by two mechanisms. One is the convection. The convection is because of the heating of the molecules of the air in your house, but at the same time, a lot of radiation is also actually coming out of this wood burner and heating up your home. In terms of industry, if we talk about, for example, glass melting or steel processing industry, so there they have a lot of big furnaces to melt the material, and here you can see that this bright section actually is the furnace, and a lot of radiation or light is actually coming out, and even if you are standing here far away from the furnace, you will still get quite hot because of the radiation that is coming out of this furnace. Also, radiation is quite important in industries, in chemical industries. So for example, this here we have a steam reforming system. So that is actually a reactor that involves a furnace. And then you have here in the reactor, you have these tubes, and in this side these tubes you have the catalyst, and actually you heat the catalyst via this furnace. So here these oval shaped things are the flames. So these flames are actually transferring heat to this tube through convection and mainly through radiation. And then once you heat up the tube, then the reaction occurs. Okay, so this is, for example, as it is showing here, that you reach up to a temperature of 300 degrees centigrade, 1000 degrees centigrade, and you need almost 300 burners. And so this is how the setup looks like. Okay, so radiation is quite important, not only in our daily life, but also in our industrial life as well. Here I put the basic concept of radiation, okay, or thermal radiation. So any object that is above a temperature of 0 Kelvin or absolute zero is going to radiate thermal energy because of the motion of the molecules. Okay, and this comes from thermodynamics or from kinetic theory of gases or fluids. So any material that actually whose molecules are in motion, they are emitting electromagnetic radiations. Okay, and this some part of this electromagnetic radiation would be the thermal radiation that carry energy, or the temperature that we feel, for example, or the increase in temperature. Okay, so so any object that is above 0 Kelvin will radiate, and if the temperature is low, for example, we might not feel that radiation, and but still, if the temperature is above 0 Kelvin, the body is radiating electromagnetic waves. And here I have shown a spectrum of electromagnetic radiation. So for example, here we have different electromagnetic rays. We have gamma rays, X-rays, UV, infrared, and finally we have radio waves. So when you go from, for example, from gamma radiation that has the lowest wavelength but the highest energy, when you go from, for example, from right side to the left side, the energy decreases but the wavelength increases. Okay, and when we are talking about thermal radiation, it's mostly from infrared region to some part of the UV region. So it's from the wavelength of 10 to the power minus ones to almost 100 micrometer in terms of the wavelength. Now, I mentioned previously that this form of heat transfer, radiation heat transfer, does not require the presence of a medium. It means that the heat can transfer in vacuum, and one of the example is actually sun heating up the earth. So for example, the radiation, thermal radiation from the sun pass through the vacuum of space, and then still we feel warmth in the on earth. Okay, so one example is, if for example, if you are if you cover your pool on a sunny day, you will feel that the radiation actually warm the pool. Okay, so I mean the cover of the pool is insulated, but despite that, the radiation can pass through it and reach your water, and then you can have a warm swim on a sunny day. Okay, so in terms of the energy, for example, being transferred from electromagnetic waves can be given, for example, by quantum theory of photons. And this theory tells us that the radiation consists of photons and light particles. Okay, so there are dual nature of the radiation. So it can be a radiation like as an electromagnetic wave, but at the same time it can have a particle nature. And this, for example, photon carries a packet of energy, and this packet of energy can be given by E is equal to h, that is the Planck's constant, times mu. So this equation here is what we call Planck's law. Okay, and this gives us the energy of the photon. Okay, at a particular wavelength, and this mu can also be expressed as a fraction of the speed of light divided by the wavelength of the light itself. Okay. So this equation can be used if we want to know how much energy, for example, a photon is carrying at a certain wavelength. The other thing, so the energy emitted from a surface that is at a temperature above 0 Kelvin depends on two main things. One is the temperature of the surface, and second thing is the nature of the surface. Okay, so if a body has a high temperature, it will emit more radiations compared to an object that has lower temperature. And also, second thing is the nature of the surface. For example, if an object is a gray body or a black body, and what are the emissivity and absorptivity of that object, and we will see that in the next slide. So in terms of the temperature of the surface, for example, here we can see that that as the temperature goes up, the wavelength is changing. Okay, so for example, if you have an object that is at a temperature of 3000 degrees centigrade, the object will be emitting infrared radiations, while if an object is at a temperature of around 6000 degrees centigrade, it will be emitting red light plus some part of the spectrum of infrared radiations. And if an object is around 30,000 degrees centigrade, it will be emitting white light. And that is one of the reasons that the sun gives us around red to yellow light, and while the stars at night that are burning actually even hotter than the sun gives us the white or blue light. Okay, so that is a direct consequence of the temperature of the surface of that object.